we're looking at ideas for solving vector proofs. And we're going to look at how putting together a simple diagram can help to form ideas before you start to look at the algebra. The first problem here comes from the Stage 6 New South Wales HSC syllabus, and I'll give you a few moments to have a look at that. We're required to prove that if we join the midpoints of a quadrilateral, we form a parallelogram. We've got a quadrilateral drawn here. It's any quadrilateral. There's no given relationship between the lengths of the sides. There's no given relationship between the angles, but these points R, Q, and P are each and so on are midpoints, which means that the distance on this side is the same as the distance on this side right throughout. So I'm going to draw up and state the problem, and then I'm going to try and develop some diagrams to give me a better idea how to proceed. I'll copy this first diagram so I can use it later. There we have it. And now to draw up the problem, I'm going to join those midpoints. And we're required to prove that we have a parallelogram. And to do that, if I prove that RQ is the same as SP and that RS is the same as QP, then I've proved it. I'll just write that up to prove. And there it is. RQ equals SP, RS equals QP. So the first thing I'm going to do is scan for vector relationships, and the markings show that here and here we have equal vectors, but they're different to every other vector, and the same thing here. Here and here we can form equal vectors, but they're different to every other. We can also see that, for instance, if we're focusing on QP, that we can form QP by adding these two vectors, and we'd end up with a 2 and a 1, and we could form RS by adding these two, and we'd end up with a 3 and a 4. So we know we're going to have to find a relationship between the 1 and 2 and the 3 and the 4. So coming down to the second diagram, and I can see that if I form a vector here and here, that we've got 1 and 2, and we can form a vector here and here with 3 and 4 segments, and we can make these equal so that we can find a relationship between the 1 and the 2 and the 3 and the 4. Let's just draw that up. I've got two vectors like that, and I've got two vectors like that. In both cases, we start with C and end with A, so CD plus DA is equal to CB plus BA. And again, just focusing on QP and RS, I can see that if I draw in QP here, because these two vectors are equal, CQ and QB, I can form a relationship between this vector and half of this side, and similarly along here. And that gives me a direction forward. I can now turn to the algebra. Before I do, what I know in the back of my mind is by symmetry, I'll find the same sort of thing on this side, and also by symmetry. Once I deal with QP and RS, then I can use the same method to deal with RQ and SP. So now I'm going to write up the relationships, and I'll just put in this vector here. RS is equal to RD plus DS, and again with vector addition, that central point D disappears, and similarly here, QP equals QB plus BP. Now I'm going to write up CB plus BA, and I can see that CB is going to have a relationship to QB, that it's twice QB, and that equals CD plus DA. And now I'm going to use that relationship 2 times QB plus BA 2 times BP equals, and doing the same on this side, CD 2 times RD plus 2 times DS. DA is 2 times DS. So we've got that equivalence, and now as I'm looking up here, I can divide this by 2. I've got QB plus BP equals, I've divided this side by 2, this side by 2. QB plus BP equals RD plus DS. Therefore, RS equals QP. And I won't go through the RQ and SP, but you can see you can apply the same thinking, and you can therefore prove both of the statements that we're required to prove.